Hi students, and welcome to Preliminary Chemistry and the Metals video series. In this particular video we're going to have a quick overview of the different models of the atom that we've I guess can identify historically, which corresponded to a lot of the important findings of what was actually inside those atoms. This is, I guess, intended to be a little bit of a revision. I'm hoping that you will have already looked at atomic models in your junior years, but we just need to focus on the main ones that are part of our historical understanding of how the model of the atom has changed. Now, one of the things that's very important when we talk about models in chemistry is the fact that because much of chemistry deals with things that are so small, it makes it very difficult for us to actually see what they're doing. So we've developed models to help us understand the behavior of different substances. And while these models continue to be useful to predict behavior or to explain behavior, then they can remain. But once they start to challenge behavior, once the behavior that we see can no longer be explained by the models, then we need a new model. So the first one was the atomic model of John Dalton. And Dalton's model was a very early model. He was the, I guess, first scientist to actually describe an atom. The idea of atoms as being the smallest units of matter is actually a very old idea, dates back to the Greek philosophers, and in fact atom has a Greek root to it. But Dalton was the one who came up with the first atomic model, and his model was basically just a solid sphere. So at this stage we have no protons, we have no electrons, we have no nucleus, no neutrons, of course, and no nucleus. So in this very first model, really it's just like a little ball, a solid sphere, and the only difference between elements was based on their differences between their atomic weights. The second model was the Thomson model. The Thomson model is based on the discovery of the electron and the fact that it has a negative charge. Now this is important because now we know that our atom is not a solid sphere, but it actually has negatively charged particles within it. That then means where are they and how are they distributed? Well, Thomson's model is often referred to as a plum pudding or a currant bun or a raisin pudding, which is a bit of a misnomer because it suggests that the electrons are all randomly distributed. And Thomson, there's some suggestions that Thomson had more of a pattern in mind to the distribution of the electrons. But the important thing is that we do have a number of different electrons, and these electrons have a negative charge, and therefore the pudding that they're in, if you like, must have a positive charge in order to balance the negative charge. We know that atoms are neutral, they're neither positive or negative. So this sort of dough, if you like, the solid part of the atom is positively charged, and it has embedded within it these negatively charged electrons. Now, we knew electrons existed, but we didn't know much else beyond this for Thomson. But very soon after this came Rutherford's experiments. Now, Rutherford's experiments were very important because there were two important components to Rutherford. Firstly, he discovered that a large amount of the atom is actually empty space. His experiments confirmed the fact that a lot of particles, when you fire them at a piece of gold foil, they pass straight through, which is suggesting that they're not running into solid spheres or lumps of pudding, but they're actually passing through space. So empty space is one important component, but what he also found was that some of those particles, those helium nuclei, which are positively charged particles, were actually being bounced back. And he said the only way that that could happen is if there was a very strong positive mass at the center of this atom that was repelling it, but most of what was around it was basically empty space. So his model is often called the solar system model or the planetary model, in which the nucleus acts like a sun and the electrons are orbiting the nucleus like planets around the sun. This explained quite a lot of behaviors and was a very good model and often still used for juniors to kind of get a general representation of the nucleus with the protons inside and electrons orbiting around it. But Bohr's model was better. Bohr realized that the electrons weren't just randomly distributed in their own little orbits like planets orbiting the sun, but they actually existed in specific levels, stable states in which they would continue to orbit the nucleus without actually moving closer to it or further away. There are some interesting implications around the forces of attraction between the electrons and the positively charged nucleus, and also repulsion between electrons with other electrons, or even the protons within the nucleus. But a lot of that is a little bit beyond this section of the chemistry course at this stage. Suffice it to say that the Bohr atomic model has a positively charged nucleus, similar to the Rutherford model, but the electrons are now occupying a stable state. So we refer to these as energy shells or energy levels, and they move between these levels on the basis of whether they absorb energy to move up or release energy to move back. And these are important considerations. And also, it helps us to explain things like the octet rule for stability. So this is particularly true of the noble gases. They have 8 electrons in their outer shell, and that confers on them levels of stability. The final one, which I don't want to spend too much time on, we've already run 6 minutes into this video, is the Schrödinger model. This is a complex model and one that we won't sort of look at too much. It helps us to explain things like subshells. This helps us to explain things like why the transition metals fill shells in a different kind of arrangement to what happens up to element number 20. And it also explains electrons that are more displaying wave properties than particle properties. So instead of being little tiny particles orbiting the nucleus like planets orbit a sun, Schrödinger suggested that instead they were more like wave particles. So some sort of duality between these two, or perhaps even just probability waves. So regions in space where you were more likely to find these electrons, or regions where you were less likely. And this created some quite interesting models that were very different to the ones that went before. These electron clouds seem to be most dense where the probability of finding electrons was higher, and less dense where it was lower. And that's given us quite a lot more complexity in our understanding of the atomic model. As long as you have a good understanding of all of these different types of atomic models and the key contributions, and of course the one that I haven't talked about is James Chadwick's discovery of the neutron, which came after this. And in fact, the Schrödinger model was probably more likely, this is from your textbook, but probably closer to around 1926 to 1935. And then Chadwick's discovery was around 1932. So that, again, updated our atomic model. But I'll leave you with that at the moment because I've gone on a little bit in this particular video. But these are the key models, the history of development of our understanding of the atom. Thanks for watching.